Hello. Today we will be talking about the Quark model of the nucleus. History of the quark. Murray Gell-Mann of the United States and Yuval Ne'eman of Israel proposed a particle classification scheme called the Eightfold Way. In 1964, Gell-Mann introduced the concept as a physical basis. Gell-Mann's model provided a simple picture in what all mesons are shown as consisting of a quark, an antiquark, and all baryons as composed of the three quarks. Most problems with quarks were resolved by the introduction of the concept of color. And over here, you'll see Gell-Mann and Ne'eman. How was the quark isolated? The scientists used a giant machine called the Large Hadron Collider. It was the world's largest and most powerful particle accelerator, and it went on for 16.777 miles. It used thousands of magnets to guide particles into each other at the speed of light. The quarks were heated up and then turned into quark-gluon plasma. When they were hot enough, they would collide, and the scientists waited for them to melt so then they could see the quarks remaining after. This was built underneath the Earth's crust to prevent any radiation that could go on. And over here, you'll see a picture of the machine. What is a quark? A quark is a gathering of subatomic particles. It has a mass and can also spin and rotate around the particles. If a quark was compared to a nucleus and an atom, the quark would be just 0.01 millimeters. The nucleus would be 10 centimeters, and the atom would be 10 kilometers. Over here, you'll see a picture of a quark. Quarks have no structure to them. They are always attached to something else. If a quark is stretched, then he is forced to stretch bigger and bigger. Down here, you will see from big to small, starting at a sandcastle, and how it ends up all the way down to a tiny little quark. The types of positive quarks and the top quark all have a charge of positive 2/3. They are called flavors when they have different names. And the negative quarks are strange, down, and bottom quarks. These all have a charge of negative 1/3. An antiquark is the opposite of the original quark. So for example, positive 2/3, the antiquark is negative 2/3. Or negative 1/3, the antiquark is positive 1/3. Where these quarks are found. Up and down are the only two quarks found in normal things. The two down quarks and an up quark make a neutron, since their mass would make 0. Two up quarks and a down quark make a proton, since the result would be positive 1. The other 4 are not yet seen on Earth, but are thought to compose some of the stars in space. We will now see a math problem.
Hello, this is Evan Maynard, and I'm going to be giving a couple of math problems and just explaining what a quark is and everything that kind of it revolves around. So, for a valence quark, you need two up quarks, or 2/3 up quarks, two positive 2/3 up quarks, and then you need one 1/3 negative down quark. This creates a valence quark, right? So, in a valence quark, a valence quark is needed to make a proton, right? So, my next drawing my next showing example, I don't really know, but what I'm drawing next is just demonstrating on how you need how the 1/2 or 2/3 then 2/3 minus 1/3 equals the charge of one proton, right? So, now, all the quarks, right, are held together by these small little things called gluons. Now, these gluons, there's tons of them, right? They're very minuscule. They're very small. We can't even see them, honestly, right? But what the gluons do is they hold the entire quark together, right? There's just so many of them, and it's just in such a vast amount, and it holds the quark together, right? These are called gluons. Now, the quark is very different or interesting because it only takes up about 1% of the total mass of the proton itself, which is a very small amount, even though it is very important to the proton itself. Now, even though it only takes up less than or about 1% of it, like 1%, it's still very important. Now, what I'm drawing next is the total number of quarks, right? Must be 2 more than the antiquarks. And then the next little snippet thing is there must be 1 more down quark than antiquark, right? This is done just to make the valence quark. That's the two. My bad. The two antiquarks that are not associated with the up quark, and the one down quark, or the one antiquark that's not associated with the down quark, makes up the valence quark, right? Now, this is done because the valence quarks came to a total of 3, and the quark antiquark pairs of the other types must all my bad. So all the basically what has to happen with all the quarks and antiquarks and pairs and other types that are surrounding the valence quark must all cancel out. They must all cancel out, right? So now next we're going to be talking about the charges of the quarks, right? And a charge must be conserved. So if a charge with a positive 2/3 appears, its partner must have a charge of a negative 2/3, right? And the spin, which is the little tail off the charge, they must also be opposite. Okay? Now, the last thing I'm trying to show is that we can't detect quarks alone, right? The more you separate the quarks, the more energy you have to put into the quarks to pull them apart. So as you do so, eventually you just put enough energy into the quarks that it just creates 2 new quarks.
Why are quarks important? Because you can look at the particle-particle interactions between protons and see that protons have an internal state that they are not elementary. A proton can absorb a photon without the increase in kinetic energy that you would expect, because some of the energy of the photon went into changing the internal state of the proton rather than all going into the kinetic energy. This can also be observed with atoms, where collision with a photon gives the atom some kinetic energy, but also kicks the electron up to a higher energy state, so that the kinetic energy is not conserved like it would be for an elementary particle. The conclusion. The quark is what makes up the nucleus, which means that it is very, very small. Only a few types of quarks have been found, and we hope we can find the rest somewhere, whether it's on Earth, or in space, or on another planet somewhere. These tiny particles are important to everything around us because they make up everything around us. And that is a quark.